So let's say that we actually have a stringed musical instrument. So we've got a stringed musical instrument, and we've got a string, and the length of the string here. Let's say that the length is going to be equal to 0.65 meters. So it's 65 centimeters long. And let's say that when you pluck this string in the fundamental mode, it oscillates and produces the note A. Okay, so this would be 220 hertz. Okay, and I want to play A sharp. That's 233.08 hertz. So it's a little bit higher frequency. So what do? Well, what I can do is I can press down on a fret, and that changes so that now only this part oscillates. That's going to be a shorter wavelength, but if it's the same tension, same speed of the wave means higher frequency. And so that would give me the other note. So the question is, I want to know delta L, how far down do I have to press? Okay, so we look at this and we say, okay, so from our basic note A, we want to figure out the wave speed. So we know that C equals lambda F. So this is the frequency 1. That's what I'm after. Frequency 2 is what I'm going for. Okay, so this would be lambda 1, F1. Okay, now what's lambda? Now, in the fundamental mode, remember the wavelength is half of L. So that means that no, sorry, get it exactly backwards. So in the fundamental mode, then the L is 1/2 of the wavelength, okay? And so that means the wavelength is 2L. So in this case, that would mean that the wavelength would be 1.30 meters. So if I plug in up here, okay, 1.3 meters times 220 hertz, this comes out to be 286 meters per second. Okay. All right. So we got 286 meters per second. It's the same string, but I want to make it shorter now. Okay. And so what I want to do is I want to have, C equals lambda F. So now it's lambda 2 F2. Okay. So lambda 2 is going to be C over F2. So that'll be 286 meters per second divided by 233.08 hertz. So lambda 2 comes out to be equal to 1.227 meters. Now, you know that L is 1/2 of that. So L2 is going to be equal to 0.614 meters. Well, the original thing was 0.65 meters, and I want it to be 0.614 meters. So that means that my delta L is going to be equal to 0.036 meters. So 3.6 centimeters down. So I press down, on a spot 3.6 centimeters from the end, and now instead of playing A with that same string, I'm also playing A sharp. Well, there's another way of doing this. Okay, we have an entirely other way of doing it. So I have this, okay, and so this is note A, okay, and that's 220 hertz, okay, and the L is going to be 0.65 meters. So that means the wavelength is 1.3 meters. Okay, none of that changed anything. That's all the same. Okay, so A, that's my F1 and lambda 1. And what I want to do is I want to play A sharp with the same string, but I do not want to have to press down. Well, what I can do is I can increase the tension. Okay, and that would change the speed of the wave. So we have that C equals lambda times F. So C1 equals lambda 1 F1. This is, nothing has changed. This is 286 meters per second from before. Okay, but I want that same length string to be A sharp. Now, A sharp is 233.08 hertz, so that's going to be my F2. Okay, it's going to have lambda 2 is going to be the same because I want it to be the same length. So C2 is going to be, lambda 2 F2, and so that comes out to be 303 meters per second. Okay. So we got a change in speed from 286 meters per second to 303 meters per second. Well, how does the speed of a wave work here? It's the square root of F over mu. So C1 is going, or I can actually square that and say C squared equals F over mu. Okay. So C1 squared is going to be equal to F1 over mu, and C2 squared equals F2 over mu. Okay. And so what I can do is I can say, what is C2 squared over C1 squared? Okay, so that's going to be equal to F2 over mu divided by F1 over mu. Okay. So the mu's cancel, so I find that F2 equals C2 squared over C1 squared times F1. Okay, so that would be equal to 303 meters per second squared divided by 286 meters per second squared times F1. And so what I find is F2 is equal to 1.12 F1. Okay. So 1.12 F1. So I increase the tension by 12%. If I increase the tension 12% to go from F1 to 1.12 F1, then I would also get A sharp using that exact same string that previously had been an A string. So that's another way of doing this if you don't want to press down on a fret. Okay. So how else could you, on that same stringed instrument, have a string, so you can actually have another string. Have them both the same tension, and have them both the same length. So make the length here still 0.65 meters. So that means the wavelength is still going to be 1.3 meters for both of them. Okay, they both have the same wavelength. Okay, but I want to use a different string. So what I can do is I can then say, okay, same thing. I know that C 1, okay, again, I mean, it's the same sort of situation here. Okay. And that is that C equals lambda times F, okay, and so I look at this once again and say, okay, I want them to have the same lambda, okay, so what I want to do is I want to change the speed again, okay, and so if they're the same length, then lambda, then C1 is still going to be 286 meters per second. C2 is still going to be 303 meters per second, okay, in order to get it, so that has not changed, but I can have a different thickness wire. So if they have the same tension, they do not have to have the same mu, okay. And so again, c squared equals f over mu. So I could then say, therefore, that c1 squared equals f over mu1, c2 squared equals f over mu2. Okay, and so then what I could do is I could say, okay, let's look at the ratio of c2 squared over c1 squared. So that would be f over mu2 divided by f over mu1. The f's cancel, so that's going to be mu1 over mu2. Okay, and so mu2 is going to be c1 squared over c2 squared times mu1. So if I plug in here, c1 squared, 286 meter per second squared, divided by c2, 303 meter per second squared, mu1, that would tell me that mu2 is 0.891 of mu1. So I could use now remember, what is mu? Mu is mass per length. And so I could use a string that has 89.1% of the mass per length, and that would also let me play A sharp using the same tension and same length string that I previously was using to play the note A. Okay, and so this is basics of using some of this idea of standing waves in musical instruments.